Let's calculate the de Broglie wavelength for dark matter. So here's the equation. We got H over mv. We're going to use H is 6.626. And we have the mass of dark matter. What should we use for that? Well, usually if you think about 10 to the negative 21 eV, that's a little too heavy. That creates this cusp pore in cold dark matter models. So that's a little too heavy. Let's go to the 10 to the negative 22 eV. That's usually what people use for smooth dark matter and stuff, and that's a general estimate for what they think that dark matter particles would be weighed. So we can use that number, and then we're going to use the velocity of the virial theorem here. So we could take the g times the mass of the Milky Way divided by the radius of the Milky Way. That's going to give us about 150 kilometers a second. So let's use that for this. It's essentially the velocity of these particles. So if we do that, then we'll get something like 2,000 light years or something being the wavelength. But what's more important is that we take a look at the next step. Regardless, let's also realize that if we wanted to take this up to one more scale up to the negative 23 eV, we'd get on the order of maybe half the radius of the Milky Way, which might be interesting. Maybe e to the 24 would give us a little bit too much there. But we could probably scale this to be about the same size as the radius of the Milky Way. Anyway, let's go to the next step. So let's take a look at the Bose-Einstein condensate, Bose-Einstein condensate that could be formed by gravitons or gravitational waves at the very early universe. And the reason is because if we're looking at the critical temperature for gravitational or gravitons to form a condensate, this is the temperature. Okay, this is the critical temperature. It's just kind of this weird formula: 2 pi h bar, Boltzmann constant, the mass here. So if we plug in some numbers, we get like some really hot temperature because the mass is super small. So the temperature is going to be really high, about 10 to the 32 Kelvin. But that's just right enough that if we get this right, that it would be perfect. This is the temperature of the Planck scale of the very early universe that happened. So you get the mass of Planck, the speed of light, and the Boltzmann constant here gives us 1 e to the 32 Kelvin. So that's basically on the same order of magnitude, which means that at the very early universe, the moment the universe, in the Big Bang, the gravitons, the gravitational waves, would have been able to form a Bose-Einstein condensate. In fact, this probably would have happened instantaneously, so they probably would have just formed. So now the question is, did the Bose-Einstein condensate persist? And for that, we have to ask ourselves, okay, over time, basically, the only reason for this Bose-Einstein condensate to even exist is because the distances inside, I think of water being inside of a box. Okay, that's essentially what we have. Water inside of a box. And the reason is because the waves, the distances between those particles, the wave functions of the particles are so small that they act more like quantum bits inside of this gigantic box, which you could think of as the de Broglie wavelength. So as long as the distances between the particles are really small, dark matter particles, which is ultra small. Okay, that's always ultra small because the distances between particles is just small. And then if you compare that to the galactic wavelength of the de Broglie wavelength, I mean, the dark matter wavelength here, the de Broglie wavelength, it's just so large that that it would make a lot of sense for this Bose-Einstein condensate to survive even at this temperature that we have here, because now that it's formed, it should still be coherent, at even a higher temperature. So so that's interesting. Anyway, thanks for watching this derivation here, and we'll see what other kind of insights we can gather about dark matter and this graviton condensate here.